Glover. I'm here to go through the light review in preparation for your light quiz tomorrow. Question number 1 asks about what is the speed of light through the cornea of your eye, which has an index of refraction n equals 1.38. And the equation we'll use is n equals c over v, where if I solve that for v, it would be c over n. C is the fundamental constant for the speed of light in a vacuum, 3 times 10 to the 8th meters per second, divided by the n value, 1.38. And if you took 3 e to the 8th power divided by 1.38, we'd get 2.174 times 10 to the 8th meters per second. For number 2, at room temperature, an underwater swimmer observes that a beam of sunlight in the water makes an angle of 31 degrees with the normal. What is the angle of incidence in air? And the n for air is 1. You should be memorizing that. And the n for water is 1.33. So I'm going to set up Snell's law, where n1 sine theta 1 equals n2 sine theta 2. I'm going to keep air's n value and my unknown sine theta 1 together, and water's n value, 1.33, and sine 31 degrees. So if I solve that for theta 1, to do 1.33 times sine 31 degrees and divide through by 1. To get rid of the sine theta 1 and just get the angle, you have to do the inverse sine. So this would be taking the inverse sine of the number that I got for this, which is 0.685. The inverse sign on your calculator is like a shift or an inverse or 1 sine to the minus 1. So if I do inverse sine of that, I get that theta 1 is 43 degrees. For number 3, a light ray initially in water with n equals 1.33 enters an unknown substance at an angle of 37 degrees to the normal. So let's say it's initially in water, where n equals 1.33, and the unknown substance, n equals question mark, it's entering that at an angle of 37 degrees, and it's refracted at an angle of 25 degrees. So if I need to calculate the index of refraction, I'm going to set up Snell's law. n1 sine theta 1 equals n2 sine theta 2. Plugging in our values, let's keep the water, 1.33, with the sine of 37 degrees, and the n value I don't know, with the sine of 25 degrees. So this one I can just divide through by the sine of 25. And solve that for n. So 1.33 times sine of 37 divided by the sine of 25. And I get n is 1.89. Once you get n, to then find the speed of light in that substance, I'm going to use n equals c over v and solve for v by taking 3 times 10 to the 8th meters per second divided by my n value of 1.89. And I would get 1.6 times 10 to the 8th meters per second. What is the critical angle for light traveling from benzene with an n of 1.501 to air? We need to use this total internal reflection formula for sine theta critical equals N2 over N1, because it's always going from a larger index of refraction to smaller index of refraction if total internal reflection is to occur. So sine theta critical in this case would be 1 divided by 1.501. So I'd get a numerical value for 1 divided by 1.501. Then I take the inverse sine of that value. Sorry. To get theta critical.
Spiritware in our front lobby from 3 until 5 p.m. today. Come and get your state championship Spiritware. Thank you.
Go PR Wolves football. Nice job, guys. So I got 41.8 degrees for the critical angle. If light travels from a piece of glass of unknown index of refraction n to air at a critical angle of 41.1 degrees, so I'm using the theta critical formula still, but I have the angle. So the sine of 41.1 degrees would equal 1 over n, because the n's on the bottom because that's where it's coming from. And from that we can get n equals 1 divided by the sine of 41.1 degrees. I get 1.5. What are the primary colors of light? That is red, green, blue. Secondary colors of light, magenta, cyan, yellow. Complementary colors, you're always going to match up the primary color with the secondary color that it's not made up of. So red is missing some blue and green, so we need to match that with cyan to get white. And remember, complementary colors form white light. Green is missing the red and the blue, so we're going to have to match that with magenta to get white light. And blue is missing the red and green, so we're going to have to add that to yellow to get white light. Cyan light is shining on a surface painted in a substance that absorbs blue light. What color will it appear? So cyan is putting in blue and green light, but this object absorbs the blue, so what's going to just be reflected is the green. So the object would appear green. Number 8, a radio frequency of 900 hertz. What is its wavelength? And the key to this problem is remembering that a radio wave is an electromagnetic wave, so the speed of light applies here. So we know that the velocity in this case is 3 times 10 to the 8th meters per second. Then we're just using v equals f lambda. So 3 times 10 to the 8th equals 900 times the wavelength, and we could solve then for the wavelength, taking 3 e to the 8th divided by 900, and I get 3.3 times 10 to the 5 meters. Okay? Then the last one here quick. Student measures the width of a strand of hair, setting up the following experiment. First a screen is set up 2.5 meters away, so that's our L variable. Second, the hair is put in front of the light source, which has a wavelength of 500 nanometers, so that would be 500 times 10 to the minus 9 meters. And the student measures the distance between the central bright fringe and the second bright spot, so that's X, to be 3.4 centimeters, or 3.4 times 10 to the minus 2 meters. And our M value would be 2, because it's the second bright spot. What's the width of the strand of hair? So we're looking for D. So my formula, if I solved it for D, D would equal L M lambda over X. So D would be 2.5 times 2 times 500 times 10 to the minus 9 divided by my X of 3.4 times 10 to the minus 2. And when you solve that, you get 7.4 times